IOD506. Analyze given information when presented with new, simple information. Right now in front of you should have the IOD506 skill sheet about strings and what happens when you hang objects from a string. You should also have emphasis, right? So you're going to be locked in the video. At any point you feel confused in the video, just press pause. Let's get started by taking a look at the background information. Many skills on the ACT require that you take some sort of information given and use it to make a new conclusion. IOD506 is an example of this type of skill. For IOD506, you will first need to examine the table, graph, diagram given in the passage. You'll then be given some new information. The test question will ask you to make some conclusions based on combining the original data from the passage with new data presented in the question. This is what's called forming a model. You can use old data to form a model of what the data is telling you. You then use that model to answer any question. Now, in order to do this, there's a whole section of analyzing this kind of information. When you create a model, you often are going to have to create some sort of equation in your head. In order to do that, you have to play a fun little logic game with yourself. You're looking at the data, and what you're going to try to do is figure out how the numbers are related to each other. So, for example, if you were given the numbers 1, 2, and 3, what you want to figure out in your head is mathematically, how could you arrange these numbers with addition signs, division signs, multiplication signs, or subtraction signs, square things sometimes, anything. You should try to figure out how they're related to each other. Can anybody figure out one way that these three numbers would be related to each other? 2 plus 1 equals 3. That's a good relationship. Anybody find another way that this would work? 3 minus 1 equals 2. Any other ones? 3 minus 2 equals 4. Want to see a crazy one? 2 minus 3 equals actually 4. Oh. Alright, but this is the idea with this. Now this is a very simple example of this, so let's check one a little bit out. Okay, we have the number 2, the number 10, and the number 20. How are these related? You can do 2 times 10 equals 20. 4. 20 over 10 equals 2. 4. Any other ones? What if you got crazy and started adding in other numbers? Right. Oh. 5 times 2 plus 2. Oh. Well, let's try this next one. How are these two numbers related? And you can add in other numbers if you need. See it?
Is it 15 divided by 2? Yeah, 15 divided by 2 and 1. 15 divided by 2 is 25 divided by 2.
Alright, 50 divided by 2 divided by 2 equals 12.5. Or, what's the easier way to say this? Nice, you can say 12.5 times 4 equals, or 50 divided by what? 4. You say 50 divided by 4 equals 12.5. Any other one? What about a decimal? Let's throw a decimal in there. Times 0.25. 10.25 equals 12.5. Cool, look at that. Okay. What if we started to do it with variables instead? Let's just start with the numbers. How are these three numbers related to? Sorry, say one more time. 12 plus 4. You can say 12 plus 4 equals 16. What I want to do now is I want to substitute out the numbers for the variables that are used. And what I mean by that is you'll just look at the number at the top of the column, and that would be what that number is. All right, so what would we say in this case? Z, because 12 is Z, plus X, which is 4, equals Y, which is 16. So what we're doing is we're actually creating an equation to relate these variables to one another based on the variables. Okay. What if we did it with two sets of data? Now I'll tell you the trick here is that whatever we make this one be, the second one also has to be true. So if it's true for the first one, it's true for the second one. Like for example, what we can see is like, okay, well, we can do 4 minus 2 equals 2. But what that would have to mean is that 8 minus 4 would have to be 2. And that's not true. All right, so in this case, it can't be the first one minus the second one equals the third one. All right, because it's, while it's true for the first one, it's not true for both of them. What do you think? So if we did 4 divided by 2 equals 2, is that true for the second one? If we did 8 divided by 4, would that equal 2? Nice. So what does our equation in this case look like? X divided by Y equals Z. Perfect. All right, you can write that any way you want. You can put them over each other. X divided by Y equals Z. It means the same thing. All right, we're starting to see where this is headed because this is big for the spring thing. How about this one? So in this case, what we're doing is we are multiplying each of these by 4 to get to the next one. So in this case, what would the equation be? Nice. We would say 4p equals that. All right. Now, this seems pretty mathematical and maybe simple in a lot of the cases, but it's interesting how few students can connect this math skill to what we're about to do. All right. Let's take a look at the data, and we are eventually going to create a model for the data that they collect. All right. This is how a lot of science is done. They'll run an experiment, collect a bunch of data, and try to figure out how those variables are equivalent to one another. What can you do for the variables to set up a relationship? All right, so in this case, passage 1 says, if left at rest, a spring attached to a ceiling will hang at its equilibrium position. If an object is attached to that spring, the spring will grow in length by a distance known as its displacement, x, measured in meters. The stretching occurs because the object applies force, F, measured in newtons, on the bottom of the spring. The spring constant K measures the elasticity, or what is known as the stretchiness of the spring. The spring has a high K, the string cannot be stretched easily. If it's got a low K, it can be stretched more easily. Various objects, all with different masses, were attached to two springs with different spring constants, and the force was measured in the trial. Once the object was removed from the spring, the energy, measured in joules, the spring needs to return to its original position, also known as potential energy, is measured. All right, so in this case, we have a set of data now. All right, what they did was they took a bunch of springs, they added some objects to it, and they measured how much was stretched, how much force was applied, and how much energy. All right, there's a lot of variables. You will notice this entire table is written in form where there's no label anywhere. It's just a variable on top of the label. So if you ever get to something like this, one of the first things you should do is start to identify what each of the variables means. So in this case, what you're going to do for each of these blanks is fill in what is each of the variables. And this is where you kind of have to go back to the passage. All right, so the first one we're going to do is K. All right, what is K? Nice, the spring constant. All right, spring constant, it says measures the stretchiness of a spring. A spring with a really high K, it takes a lot of effort to pull it apart. Think of a coil inside of like a car part would be this way. All right, whereas a spring with a low K is real easy to stretch, like a slinky. If anyone's ever played with a slinky before, you can pull on the end of it, and it moves really easily. All right, what about X? What is X? Displacement. Nice. Stretch. What is F? Force. And what is PE? Potential energy. All right, now the reason that we do this is because the questions won't give you the variables. The questions won't give you the description. So it would say things like, what was the displacement of the spring in trial 1? You need to figure out that displacement is X. So in order to do that, you have to go back to trial 1 and look at the X value in order to get the displacement. So that's kind of the power in starting to name some of these. You know what the question's talking about. The other useful thing is to figure out what the units of each of these are. Because sometimes what you'll find is that your answer choices have different units. If your question is asking you for energy, for example, if you knew what the units of energy were, you actually could eliminate some possible answer choices because they weren't in the right units. All right, so let's take a look at each of these. You'll notice that in the question, so now we're on question 6, it says another problem tables have is lack of units. But the hint at the end is that one of the 4 variables is unitless and does not have units. All right, in this case, let's work our way up. Potential energy. What are the units of potential energy? Joules. Nice. We go back here. It says the energy measured in joules, the spring used to return its equilibrium position. All right, go here. Right up. All right, what about force? What's the unit of force? Newton. Excellent. It's force measured in newtons. What about displacement? Nice. Meters. If you go over here, the distance is known as displacement measured in meters. What about the spring constant? Yeah, this is our unitless one. Spring constant is two of the same unit divided by one another, so they cancel. So in the end, there's actually no units of spring constant. All right, we are ready to tackle this. Okay. All right, if we take a look at the example question, it says it was discovered that the metal in the springs that were used in this experiment can only safely withstand 30 newtons of force. Which of the trials would have been unsafe to perform? All right, what are we looking for? We're looking for the trials that are what? Nice. And newtons would be which column? F. All right. We know that force is measured in newtons, so we're looking at any of the force column that is greater than 30. Are there any where the force is greater than 30? Which two?
Trial 3 and F.
Nice. Both of those 250s are above 30. Those are unsafe trials to perform. All right, what you want to do right now is you want to answer questions 7 and 8 together in your groups. All right, if you're watching this video at home, answer questions 7, 8 right now. And you should press pause. Press play when you're ready to go through the answers. All right, you should press play at this point if you are ready to go through 7 and 8. If you're still not ready yet, still time to press pause. Question number 7. How much force did object 3 exert on the spring with the lowest spring constant? Now, this is a pretty wordy question for a pretty simple case. All right. In this case, we always try to figure out what are we looking for. All right. What are are we looking for? What variable are we actually looking to answer here? Nice. All right. And if it helps you, this always helps me whenever I do this kind of passage. I always circle the thing I'm looking for. Because in the end, that's the one that I always want to make sure that I'm answering. Because a lot of these questions, it's easy to put the wrong variable. All right. So we're looking for a force. So we have all of these options right here to choose from. All right. Now, which force do we pick? We see there's a couple of 5s, there's 25s, and some 50s. How do we know which of those 3 we should pick? What do you think? Okay, so object 3, it's either 50, or there's another object 3 where it's 50. And which one's the lowest spring constant? Well, which one, so which letter is the spring constant? K. So which one has a lower K? This is trial 3, or this is trial 6? Which one has the lower spring constant? 3. So what we're actually looking for is this number right here. All right, now if you were going through it, you actually would figure out that they're both 50. So either way, you wouldn't actually need to go any further, because the right answer is 50. 50 bananas?
50.
Oh, no, no. 50 newtons. Okay, let's take a look at the next one. If you apply 5 newtons to a spring with a spring constant of 10, how far would the spring stretch? What are we circling in this case? What are we looking for? Okay, how far it would stretch, and which variable letter is that then? X. The displacement is how far it stretches. So actually, I'll switch to another color. So the stretch is what we're looking for, and that should be found somewhere in here. So now we have a lot of different options. 1, 5, 10, 0.5, 2.5, 5. It's going to be one of those, but which one is it? All right, so we're applying 5 newtons, which means we have to look at the force column, and 5 is here, and 5 is here. Sorry, green or something written. So now our answers are either going to be 0.5 if it were that one, or 1 if it were the first one. How do we know if it's 1 or if it's 0.5? Right. Spring constant 10. This one here has a spring constant of 5, so that can't be our answer. This one here has a spring constant of 10. Boom. There's our answer. 0.5 apples. Meters. All right. What you want to do right now is think back to all those experiments that we were looking at the start of class. This is why we practice those things. Questions 9 and question 10 ask you to find a relationship between, the first one is K, X, and F. The second one is P, E, and F. All right, so take about 2 minutes right now and see if you can go through, look at all the data that you have in your trials, and try to first figure out a relationship between K, X, and F. And the second relationship you want to see if you can find between P, E, and F. Okay, when you are ready to see if your relationship is right, press play. Right now, you should pause. All right, if you're pressing play at this point, that means that you have discovered both formulas for 9 and for 10. So just like we did in the practice, what we want to do is first we're going to come up with a relationship that relates K, X, and F. What we're doing here is creating what's called a model. All right, we collected a whole bunch of data, and now we're trying to figure out what the data means. We're then going to use this model to answer all of the other questions once we have this formula written down. So if we look at K, X, and F, all right, just like we did in the practice, like the first one we have is 5, 1, and 5. Now with every equation we come to balance 5, 1, and 5, that equation also has to work for 5, 5, and 25. All right, so what do we get that works for all of these all the way down? If we take 5 times 1, we get 5. If we take 5 times 5, we get 25. Take 5 times 10, we get 50. Take 10 times 0.5, we get 0.5. Take 10 times 2.5, we get 25. And 10 times 5 equals 50. And that works for the whole way through. So our model is going to say that K times X equals F. If we know this one equation, we can now answer every single, well, along with the second equation, we can now answer every single question on the rest of this page. All right, let's take a look at it. The second equation asks us to find the relationship between PE and F. Now the hint tells you that assume that numbers won't line up perfectly. Remember, in an experiment, because now we've all had a lot of practice doing experiments, numbers don't always come out perfect. So you have to allow them for a little bit of wiggle room that normal experimentation taking place. So we're trying to figure out how 5 is connected to 2.4, 25 is connected to 12.5, and 50 is connected to 25.2. What do you think?
F divided by 2
Excellent. So you're saying 5 divided by 2 equals 2.4? Right, because it actually equals 2.5, but it's really close. It's close that it would not be a significant difference. All right, the same thing's true for 25. 25 times 2 is actually directly equal to 12. 50 times 2 is, or 50 divided by 2 is 25, which is very close to 25.2. And the same would be true all the way down. What we would say is there's a couple different ways you could write it. PE is equal to 0.5 times F, PE is equal to 1/2 times F, PE is F over 2, if you want to say it that way. Any of those ways, they all mean the same. All right, now that you are armed with your equation for 9 and your equation for 10, you can answer every single other question on this page. You want to start by doing 11 and 12 first, and press play again after you've done 11 and 12, and then we're going to go on and do the last ones. Try doing 11 and 12 together. Now remember, it's just like simple physics that you did freshman year. All right, just fill in the variables. Figure out what variable you're looking for, what variables you know, plug them into your equation, and boom, you are done. Press pause now. All right, if you're pressing play at this point, then you are ready for questions 11 and 12. So let's get started with 11. A new object, object 5, is attached to a new spring with a spring constant of 20. And the spring, it should say, stretched 1 meter. All right, and the question is, how much force will be placed on the new spring? Our answer should be a what? What are we looking for? For A, we're looking for a what? A force. All right, how much force? Force is what letter? F. Now, using our equation, what do we know that F is equal to? K times X. So F is equal to K times X. We're looking for F. What is K in this case? 20, because it's the spring constant. So we put 20 in here. And what is X? 1, because it's stretched 1 meter. 20 times 1 gives us a force of what? 20 bananas. Okay, let's go to the next one. How much potential energy will be used to bring the spring back to its original position? We're looking for a what? Potential energy. We know that potential energy is equal to what? Yeah, PE is equal to 1/2 F. Now we also, what is our force? 20, we already found it. Plug that in for F. We get 10 joules. Good. Let's try it again. Now this one's tricky because now we're changing the scenario again a little bit. We're using new information to make a prediction based on a model. A new trial was conducted where 2 object tubes were attached to the spring used in trial 1. All right, what would you expect the displacement of this trial to be? So what are we looking for? Displacement, which is what? X. All right. We know that our formula is Kx equals F. So if we're looking for X, the 2 things we then need to figure out are F and K. Which one do we want to do first? Yeah, what is F in this case? Okay, so object 3 is what it tells us, is what's exerting the force. So how much force does object 3 exert? 50. If we look at object 3 both times, we'll see that no matter when object 3 was used, it exerts 50 newtons of force, because the force is coming only from that object. All right. However, how many object 3s are we using? 2, which means what is the actual force? 100. So in this case, we should have 100 there. So now we have an F value of 100, which is 2 object 3s. But what's the K? How do you get 10 for the K? The rest of the question tells us it's the spring used in trial 1. Not 15. What was the spring used in trial 1? 5. Yep. So the trial 1 is here. The spring used in trial 1 had a spring constant of 5. Which means all we have to do is now plug 5 into here. 5x equals 100. Divide both sides by 5. Cancel, cancel. Equals 20. 20 displacement, which is 20 meters. Excellent. Okay. Now, how much energy would we use to bring the new string back to its equilibrium position? What are we looking for? Potential energy. All right, we know our equation for energy is PE equals 1/2 F. What's our F in this case? 100, because we found that up here. Plug that in for F. 1/2 of 100 equals 50 joules. Fantastic. Huzzah! Okay, at this point you want to finish the rest of the sheet. Go all the way through. When you have finished the rest of the sheet, you should press play again and we'll go through the rest of the answers. By this point, the rest of these problems should start to sail now that you've had some experience working with these kind of questions. Again, you should press pause now, press play when you're ready to go through the answers. If you still feel confused, you should rewind. Alright, if you are pressing play at this point, that means that you are ready to go for questions 13 to the end of the passage. So let's start with 13. 13 gives you a new scenario. You've already built the model. In your head, you've built the model on the paper that says that K times X equals F. You've already built the model that PE equals 1/2 X, or 1/2 F, sorry. Alright, so you can't forget the two models we've already built. So now if we use that model for the new situation, the ball that drops in Times Square in New York in New Year's Eve is actually hung from a spring, not a rope. The spring that the ball hangs from has a spring constant of 30. The spring's displacement is 20 meters. How much force does the ball exert on the spring? Our answer should be a what? What are we looking for? Force. So circle force. So if we use our equation, K times X equals F, we need to find the force, which means we need to know K and X. What's K in this case? 30, because it's got a spring constant of 30. And what is X in this case? 20, because the displacement is 20. 30 times 20 gives you a force of what? 600. How much potential energy is stored in the spring? We're looking for potential energy. We know that PE equals 1/2 F. So PE equals 1/2, and what's our F? 600. We just found it here, plug it back in, and we get 300 joules. Delightful. Number 14. Spring mass combinations that have the highest stored potential energy are the best pairs using pistol trigger. That combination of spring mass from which trial would make the best pair to use as a trigger? Now this one's tricky, all right, because we're not looking for mass and we're not looking for a spring. What are we looking for? A potential energy, all right? So spring mass combinations that have the highest stored potential energy are the best used for pistols, for pistol triggers. So which one of these has the highest potential energy? 1, 3, 5, or they're all the same? Nice. 1, 3, 5, and 25.2 is the biggest one of all. All right. Now this one can frustrate some people. You stretch an average Slinky, which is a spray toy, the one that goes downstairs and goes in there for your neighbor's dog. All right. If you stretch it more than 7 meters, it won't return to its original shape. I don't know if you've ever played with a Slinky before, knows this. If you stretch it too far, then it's broken, and then it doesn't work anymore. All right. Which trial would have ruined Slinky? What are we looking for in this question? How do you get displacement? It is displacement. Nice. Meters is a great trigger right there that should tell you this is what we're looking for. We're looking for meters. All right. And also, we're looking for the stretch. All right. Not stretchiness, but how far it's stretched, which is the difference between K and X. All right. Now we're looking for one that would have ruined the Slinky. What do we know then about the stretch? Right. If the stretch is greater than 7 meters, if the displacement is greater than 7 meters, we should say it ruins the Slinky. So which trial would have ruined Slinky? Would it have been the displacement of 1, 3, 5, or none of them would have ruined the Slinky? Is it the only one that's greater than 7? I like that. And last but certainly not least, one thing you need to know before going into this is you can never, ever, ever ignore data. And you can never, ever, ever throw out data. If you run an experiment and you get data and it doesn't match what you've already found, the only thing you can do is rerun it. Either you made a mistake your first time or you made a mistake your second time. Right? You can't do the same thing twice in a row and get different results. So, how would the scientists find the impact if another spring with a constant of 20 stretched 5 meters and the force used was measured to be 50 newtons? How do you set up a problem like this? What do you do with all the data that you're using? Yeah, plug it into your equation. So we're going to try to see if our model that we made, which is K times X equals F, does it still work in this scenario? K is 20. X is 5. F is 50. Does 20 times 5 equal 50? No, we just broke our model. All right, so we know that it is not consistent with current findings. We also know you can't ignore it and throw it out, so that C and D is out. The only thing you can do, rerun. Do it back. All right, if you understood all of these problems all the way through, that means you are ready to rock out a quiz. If at any point you feel like you are a little bit confused, especially with how to create the formula or how to use the formula, you want to press rewind now, go back, try the question again. If it's quiz time for you, good luck.